Dear students and learners, in this class, we discuss about basics of real analysis. Already we studied the subject real analysis, but in this class, we just recall the basics of real analysis. First, we have to know what is a set. Can anyone answer? A set is a collection of well-defined objects. Well-defined in the sense a particular element either is in the collection or not in the collection. For example, consider the set of collection of all vowels A, E, I, O, U. This collection is clearly well-defined because for any alphabet, we can say a particular alphabet belongs to this collection or does not belong to this collection. For example, consider the alphabet B. B does not belong to this collection. Similarly, consider the alphabet I. I belongs to this collection A. So, this collection is a well-defined and hence is set. Another example is the set of all students in first MSc. This moment, you have one question. Which collection is not well-defined? Can anyone answer? Okay. Consider the collection of all beautiful girls in first MSc. This collection is not well-defined because beautifulness may differ from person to person. So, this collection is not well-defined. Can anyone say another example? Okay. The set of all tallest girls in first MSc, the set of all intelligent students in first MSc, these collections are all not well-defined and hence does not is set. Next one is number system. Already we know that this number system, we just recall the collection of all numbers from 1 to infinity is said to be natural numbers and is denoted by n. The collection of all numbers from 0 to infinity is said to be a whole numbers and is denoted by the symbol w. If we include negative numbers, that is minus infinity to plus infinity, 0, 1, 2, 3, etc. Similarly, minus 1, minus 2, minus 3. This collection is said to be an integers and is denoted by z. If the number is of the form p by q, then that collection is said to be a rational numbers and is denoted by q. If the set of all numbers in this world are said to be real numbers, this is denoted by r. If a number which is not a rational, then that number is said to be a irrational. Irrational numbers are root 2, root 3, root 4, root 5, etc. If there exists a negative number in this row, then it does not represent a real number. And hence, we can extend this real number into a complex number. A complex number means C equal to R union I and minus I. I means square root of minus 1. Okay, square root of minus 1 equal to I. Okay. The diagram for this number system is smaller set n, set of all natural numbers, and then whole numbers, and then set of all integers, and then set of all rationals, and then set of all real numbers. In this diagram, we can say that n is a subset of w, w is a subset of z, z is a subset of q, q is a subset of r. Next one is types of sets. The first type is empty set. Empty set also named as void set or null set. Empty set means a set having no elements and is denoted by pi. Next one is subset. Consider the set A and B. If the elements of A are also the elements of B, then A is said to be A is a subset of B. It is denoted by this symbol. Next one is proper subset. Proper subset means if at least one element of B which is not in A, then A is a proper subset of B. It is denoted by this symbol. Next one is improper subset. Improper subset means empty set and itself. That is, if we consider the set A, then pi and A are the improper subset of A. Okay. Consider this example. A equal to 1, 2, 3, 4, 5, 6. B equal to 1, 2, 3, 4, 5, 6, 7. A is a subset of B because all elements of A are also the elements of B. And also, A is a proper subset of B because at least one element 7 of B is not in the set A, and hence A is a proper subset of B. We know that what are the operations on numbers. There are 4 arithmetic operations on numbers. They are addition, subtraction, multiplication, division. Likewise, there are some operations on sets. The first operation is union. Consider 2 sets A and B. The union of A and B is the set containing all elements of A and B. It is denoted by this symbol. Next one is intersection. The intersection of 2 sets is the set containing elements which are common to A and B. It is denoted by this symbol. Next one is complement. A complement of a set is the set containing elements which are not in A but in the universal set U. It is denoted by a complement. It is a unary operation because we need only one set to perform this operation. But to perform union and intersection, we need at least 2 sets. And hence, union and intersection are binary operation and complement is the unary operation. Another operation is difference. A set containing elements which are in A but not in B. It is denoted by A minus B. Next one is indexed family of sets. Let lambda be a non-empty set. Non-empty means there exists at least one element. Then the collection of sets A lambda such that lambda belongs to del is said to be a indexed family of sets. And the set del is said to be indexed set. Because the collection A1, A2, etc. are indexed by the set delta, and hence this collection are said to be indexed family of sets. This collection is infinite. That is A1, A2, etc. up to infinity. The diagram called Venn diagram, this diagram is familiar with us. Consider 2 sets A and B. This circle represents the set A and this circle represents the set B and the rectangle represents a universal set. Then A union B is the set containing with the elements of A and the elements of B. That is, the blue color represents the set A union B. A union B is the set containing both A and B. That is, A is a subset of A union B and B is a subset of A union B. If any one set is a subset of the other, then the A union B will be equal to the larger set. For example, if B is a subset of A, then A union B will be equal to A. In this diagram, we see that B is a subset of A and A union B will be equal to A. If A is a subset of B, then A union B will be equal to B. These results are used to prove theorems. Next one is intersection. A intersection B is the set containing the common elements of A and the elements of B. Common elements of A and B is this portion. So, this portion represents the intersection of A and B. A intersection B is a subset of A and also subset of B. That is, Generally, A intersection B is the set contained in both A and B. If one set is a subset of another, then the intersection will be equal to the smaller set. That is, if B is a subset of A, then A intersection B will be equal to B. In this diagram, B is a subset of A, therefore A intersection B equal to B. If A is a subset of B, then A intersection B will be equal to A. In this diagram, A is a subset of B, so A intersection B will be equal to A. Next one is complement. The complement of A is denoted by green color. That is, A complement equal to U minus A. And A minus B is this portion. A minus B are also written as A intersection B complement. Next one is relation. We come across many relations in our life, like mother, father, sister, brother, friends, etc. In general, relation means the way in which two or more things are connected. By mathematically, a relation on A is a subset R of the Cartesian product A cross A. Next one is functions. Another name for functions is mappings. There exists a rule F which associates to every element X in A unique element f of x in B. That is, for every element in A, there exists an unique element in B, then that rule is said to be a function. The set A is said to be a domain, B is said to be a codomain, and for each x in A, the f of x is said to be the image of x. And the set R equal to set of all f of x such that x in A. This can be written as f of A. This set is said to be a range of f. Consider this diagram. We have two sets A and B. A contains A, B, C, D, E and B contains 1, 2, 3, 4, 5, 6. Okay. For each element in A, there exists a unique element in B and hence this situation represents a function. This is also represents a function because for each element in A, there exists a unique element in B. D has a unique image 4. E has a unique image 4. That is, 4 has 2 pre-images. This situation represents a function. But if this situation occurs, that is, B has 2 images, 2 and 3. This is not a function. Example, consider the set R equal to 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. This collection defines a relation A is less than B on A equal to 1, 2, 3, 4. Another example is R equal to set of all x, y such that x is a descendant of y. Descendant means valithondral. Okay, on the set of all people. This situation represents a relation and if y is a father of x, then that situation represents a function. Another example, input, output. The relation between input and output represents a relation if for each input there exists a unique output that represents a function. In this slide, you have to know what is a ordered pair. Ordered pair, unordered pair. Ordered pair means the pair x, y is not equal to y, x. And unordered pair is the pair x, y equal to y, x. For example, consider the distance between 2 points x and y. This distance represents a unordered pair because the distance from x to y is same as the distance from y to x. So, this pair is unordered pair. If we consider the pair 1, 2 in Cartesian product, then that is the ordered pair because 1, 2 is different from 2, 1. Okay, next types of functions. There are several types of functions. The first function is one-to-one. One-to-one also named as injective function. A function is said to be one-to-one if every element of A has a distinct image. That is, if f of x equal to f of y, then x equal to 1. Next one is onto function. Onto function is also named as surjective. Onto function means for each element in B, for each element in codomain, there exists a pre-image. In other words, if the range of the function will be equal to the codomain, then that function is said to be a onto function. Next one is one-to-one and onto. That is, a function which satisfies one-to-one as well as onto is said to be a one-to-one and onto function. Another name for one-to-one and onto function is bijective one-to-one correspondence. Next one is into function. Into function means there exists at least one element in B has no pre-image. In this example, 6 has no pre-image. That's why this function represents a into function. Next one is many-one function. Many-one function means at least two elements of A has same image. In this example, D and E has the same image 4. So, this function represents a many-one function. And another function is identity function. Identity function means a function maps into itself. That is A to A. A to A, B to B, C to C, D to D. This function is the identity function. This function can be defined as f of x equal to x. That is, a function maps the element into itself. Another function is constant function. Constant function means all elements of A maps the particular element k. That is, f of x equal to k for all x belongs to A. Similarly, in this identity function, f of x equal to x for all x belongs to A. Next one is finite and infinite set. Finite means empty set is said to be finite, or if there is a one-to-one correspondence between A and the set 1, 2, etc. n. That is, if the set containing a finite number of elements, then that set is said to be a finite set, otherwise infinite. For example, the set 1, 2, 3, 4 is a finite set and the set 1, 2, 3, etc. infinite is infinite. Next one is countably infinite. Countably infinite means there is a one-to-one correspondence between the set and the positive integers. Example, the set of all integers, the set of all rational numbers. Next one is countable and uncountable. A set is said to be countable if it is either finite or countably infinite. Otherwise, the set is said to be uncountable. For example, 1, 2, 3, 4. This set is said to be countable because this set is finite, and ZQ are also countable because these sets are countably infinite, and R is uncountable. Next one is neighborhood of a point. If there exists an open interval I containing P and contained in the set, that is, P belongs to I belongs to N. For example, consider this point P. This P belongs to the interval minus epsilon comma plus epsilon, and I is a subset of N. This is the definition of neighborhood in one-dimensional. In two-dimensional, if P is a point, then neighborhood of N is this one. Example, every open interval a comma b is a neighborhood of each of its points. Similarly, a closed interval a comma b is a neighborhood of its points except a and b. Next one is interior point and interior of a set. If S is a neighborhood of P or neighborhood of P is contained in S, then the point P is the interior point of S. Interior of S is the set of all interior points of S. Clearly, interior of S is open. Next one is open set. If S is a neighborhood of all of its points or all points of S are interior point of S, then the set is said to be open. In other words, interior of S equal to S, then the set is said to be open. Example, the intervals open interval a comma b, a comma infinity, minus infinity comma a are all examples of the open set. Next one is limit point and derived set. If every neighborhood of a point P contains infinitely many points of S, then that point P is a limit point of S. The set of all limit points of S is said to be a derived set of S. Next one is closed set. If each of its limit points is a member of S, then the set is said to be closed set. And the closure of S is equal to S union the set of all limit points S dash. Example, the intervals closed interval a comma b, minus infinity comma closed a comma infinity, finite set are all examples of closed set. We know that union of two open set is open. Similarly, union of two closed sets is closed. That is, union of finite number of open sets is open. Similarly, union of finite number of closed sets is closed. Arbitrary union of open set is open, but arbitrary union of closed sets need not be closed. For example, consider the intervals in equal to 1 by n comma n. In equal to 1 by n comma 1, where n belongs to natural number. But the union of these collection will be equal to open 0 comma closed 1, which is not closed. Similarly, the intersection of two open sets is open, the intersection of two closed sets is closed, the intersection of finite number of open sets is open, the intersection of finite number of closed sets is closed, arbitrary intersection of closed sets is closed, but arbitrary intersection of open sets need not be open. The counter example is in equal to minus open interval minus 1 by n comma 1 by n, where n belongs to the natural number, but intersection of in will be equal to 0, which is not open. Consider this example. First example, 1 by n comma 1. Closed interval 1 by n. Substitute any value for n. We have first one is 1 comma 1. Second one is 1 by 2 comma 1. Closed interval 1 by 2 comma 1. Third one is closed interval 1 by 3 comma 1, etc. If we union all these sets, if we union all these closed sets, we have open 0 comma closed 1, because 0 is not included in this set. That's why we have the set open 0 comma closed 1. This is not a closed. Similarly, if we consider minus 1 by n comma 1 by n, the diagram of this intervals is this one. If we substitute 1, 2, 3, etc. for n, then we have so many open intervals, minus 1 by n, minus 1 comma 1, minus 1 by 2 comma 1 by 2, minus 1 by 3 comma 1 by 3, etc. If we intersect all these open intervals, we have only 0. This is not open, and hence arbitrary union of closed sets need not be closed. Arbitrary intersection of open sets need not be open. Thank you.